Since we didn't really have any questions, let's start working. So, as a reminder, when we talked about integration, we related integration to a summation, adding a bunch of pieces together. We primarily use this to discuss area problems. And we've used it to now apply to both areas of strange spaces using curves, areas between curves, and now extending the area into another dimension using a volume problem. There's one final application of integration that's pretty common, and this one is specifically dealing with arc length. Now, the idea of arc length is pretty straightforward. The formula is not. So here we go. Define arc length. The formula is S, which stands for arc length, is equal to integral from a to b of the square root of 1 plus the derivative with respect to y of the function squared dx. So as weird as this sounds, I want to explain what this function does. So first of all, we have boundaries, right? My left bound, my right bound, indicating where I'm going to start and stop my curve. We have here y prime, which we know of as the slope generating function. Notice that we're taking that y prime and modifying it by doing a couple things to it. We are squaring y prime, adding a constant to it, and square rooting the results. In fact, if you look very carefully, this actually looks a lot like Pythagorean's theorem. Just missing one square, and in fact that's where this function came from. It uses a modified version of Pythagorean's theorem, assuming one of the values stays constant. So, what this is doing is using the slope to predict how long the function is going to be, which makes a lot of sense. If you think about it, the slope is the change, and when we talk about the physics applications of integration and derivatives, you can work backwards from change to determine distance. This is just a special way of doing so, using a very specific version of a formula. So with this, we can determine the length of any arc as long as we can determine y prime, and from there, integrate this function. Now, this does not obviously work for every single function, and much of advanced calculus is learning how we can find more advanced integrations of these functions that don't fit our current techniques. Obviously, if our function is not very nice, such that we cannot use a u substitution or something else, this becomes very difficult to do. So I'm going to use some examples in the book that do work, but this will not solve every function with the tools we have. If you want to solve other functions, you have to get more tools. You have to have more ability to integrate with weirder and weirder functions, getting more and more unique results. Here we go. This one, we need to go to examples from the text. We're going to determine arc length of the following situations. I'm going to get as much as I can of this. Leave that right there. There we go. We're going to determine the arc length of the following curve. So, y is equal to the natural log of the sine function, and we're testing this between pi over 4 and 3 pi over 4. First of all, this is a weird function to begin with, so I'm going to actually graph this with Desmos first. Then we'll talk about what that arc length is going to look like, and then we'll actually compute it using this formula for S. Here we go. Let's first start by looking at, well, what this function looks like. Because it's a natural log function, and so that can be kind of weird to see how it's supposed to fit together. As it turns out, this function does some really weird stuff because of the natural log and sine specifically. Here we go. Desmos, tell me, oh great, wise and powerful Desmos, what does this function look like? Well, I use natural log of the sine function. Oh, great and powerful Desmos. Now, we are looking specifically between pi over 4 and 3 pi over 4. Pi over 4 would begin right about here. 3 pi over 4 ending right about there. So we'll be measuring this part of an arc, which, as you can see, has a somewhat semicircular shape. You could probably estimate it reasonably with a semicircle, but obviously we couldn't get an exact answer without more information. So let's attempt to use this integration technique to determine the arc length of that particular function. And if you want to see more examples, I can post examples, but again, I will not be requiring any examples specifically for your homework. Here we go. Function. Yep. Okay, to find the arc length, we need to know a couple things. We need to know A and B. Well, that's pi over 4 and 3 pi over 4. We need to know what y prime is so we can plug it into this function. So I will be taking that part next. And then we're going to plug all that in and find our arc length. Here we go. So my arc length S is equal to the integral of pi over 4 to 3 pi over 4 square root of 1 plus my derivative squared dx. So what I got to do is plug in the derivative and see what happens. Well, let's see what we do. I come over here, on the side over here. I'm going to take the derivative with respect to x of the function, the natural log of sine of x. Okay, so first, it's a chain rule problem. This is a chain rule. We do the outside function first. As a reminder, the derivative of the natural logarithmic function, so ln of u, is u prime over u.
In the office.
So my u in this case is sine, so that goes there. My u prime is cosine, because the derivative of sine is cosine. So I end up with my derivative is equal to cosine of x over sine of x. Which, if I remember from trigonometry, this is actually something unique. Cosine of x over sine of x. This is cotangent. Yay! Cotangent. Yay! Cotangent. I don't know. Alright? Which means, over here in my formula, I can now put in cotangent of x quantity squared. Now, this function does not match any of my cheat sheet problems. However, if I remember one of my Pythagorean theorems, or one of my Pythagorean identities, there is a way to fix part of this problem. So again, this function by itself is not solvable without knowing some trick. So I'm going to go to my Pythagorean cheat sheet, and it states that 1 plus cotangent squared is something else. 3 pi over 4. This becomes the square root of cosecant squared of x. So I first have to get the actual function right, and then I may have to make some modifications, either algebraic modifications or trigonometric modifications. But it gives me this version of the formula. Now I simplify algebraically because a square and a square root naturally cancel. And then with the integral from pi over 4 to 3 pi over 4 of just cosecant of x dx. And what is the integral of cosecant of x?
Negative cotangent u plus c.
Negative cotangent of u's, in this case my u would be x, plus c, but we're doing a definite. So it'll be negative cotangent of x from pi over 4 to 3 pi over 4. So that's how all these pieces kind of just fit together very nicely. Now I plug my two values in, subtract the results, and I am finished. The arc length of this function is equal to negative cotangent of 3 pi over 4 That's my first piece, minus negative cotangent of pi over 4. I simplify what I can. Let's see. Negative cotangent of 3 pi over 4. So cotangent of 3 pi over 4 would be negative 1. Negative of that would make this positive 1. Minus cotangent of pi over 4 is 1. Negative of that would make that negative 1, so I'm subtracting a negative 1, so that would become plus 1, and we end up with the very simple problem 1 plus 1, which is 2. So I'll scroll back and kind of showcase my work as I did went through it. We'll do another example here in a moment, but this is the main process. It's just knowing the formula and how to plug into it that's going to be the tricky part. And of course, it can use any of the previous rules to solve it. So from the beginning, I took my original function. I plugged in my values, my boundaries. I plugged in 1, which is in the formula, plus, which is in the formula. I then need to take the derivative and square it. So over here, I took the derivative, which involved doing a chain rule problem, got the derivative. I rewrote the derivative as cotangent of x using a trig property. I plugged it in. I wrote it again, in this case, 1 plus cotangent squared using another trigonometric property to get to here, which is pi over 4 to 3 pi over 4 of the square root of cosecant squared of x. I then square and square root cancel, leaving me with this version of the problem, which has a very simple solution as long as I remember it. The integral of cosecant is negative cotangent, and then I plug in my two values, simplify, and I am finished. As a reminder, if this was a calculator portion test, you could have gone all the way back to here and just plugged this into the calculator. Okay? On the calculator portion of the test, take as many shortcuts as you can, unless the problem says to show your work. A lot of them are multiple choice. Like, use that. Help yourself. Many of the calculator questions, the calculator is not incredibly helpful because they'll put like variables in it or something weird where it can't do it directly. Like this one, you couldn't start from the beginning and just do it directly. You had to be able to take the derivative yourself and then plug the derivative in. But once you're to this point, calculator can do the rest of it. Okay, so just to showcase that, I will type this in the calculator and make sure I get 2. I will do the integral from pi over 4 to 3 pi over 4 of 1 plus cotangent of x squared, square rooted dx. Here's my calculator. Whoop. Yay! I go to the math tab. I'm doing a finite integral from pi over 4 to 3 pi over 4 of the function, the square root of 1 plus cotangent, which is the inverse of tangent, so 1 over tangent of x squared dx. This is the other annoying part about a lot of the trig functions, is that they're not always pre-programmed. I should get 2. I'm in degrees, damn it. I mean, shoot. Why did I get the wrong answer? Did I calculate myself? We'll go back, we'll take a while. I'm really sure that's what I see. This is my entire sheet. Oh, simple. Michael, you told me the wrong thing to do.
What? You took the integral of cosine. I gave you an integral of cosine, right? Is that okay? Fair enough.
Michael! Michael!
Sorry.
I didn't catch either, so. Okay, I'm betting it's a little less nice at the end because we got a weird answer when I plugged the factor. Okay, what is the integral of cosecant? Just cosecant.
So we can actual. Oh, there it is. Negative cosecant.
Is equal to?
It's cosecant plus c.
Alright then.
Oh, wait, no, it's cosecant to theta. What the heck? Is there just an integral of cosecant?
What the heck? Why would you make the right answer? Okay, I will double check my work. I don't like getting the wrong answer. Okay. The derivative of a natural log function is u prime over u. So u prime, derivative of sine is cosine, over u, sine is sine. Cosine over sine is cotangent. So far up to here, I don't believe I've made any mistakes. Okay. I go to my Pythagorean formulas, Pythagorean identities.
Oh, I gotta write cosecant right there. Ah, I see. Why do you Alright, I've got the integral of cosecant.
What is the name of cosecant?
Alright, it's just negative natural log of the absolute value of cosecant x plus cotangent x. We gotta write it down on the paper, I just now noticed.
It's not included on the paper, is it?
It is not.
Dang it! Curse you!
You're welcome. Led you the wrong way.
Okay, so go ahead and integrate this for me. You said it was natural log, absolute value.
Negative natural log.
Oh, negative natural log.
Cosecant u plus cotangent u.
So cosecant x plus cotangent x.
X.
Okay, evaluated from pi over 4, 3 pi over 4. So my solution would be negative natural log, absolute value, cosecant of 3 pi over 4 plus cotangent of 3 pi over 4 minus negative natural log of the absolute value, cosecant of pi over 4 plus cotangent pi over 4. And apparently that's 1.74. Dang you, Michael. I thought it was on there. I have to do use substitution to prove that. So, it's fine. Okay. Let's do another one. No trig functions this time. Let's see. Yeah. Yeah. Okay. We are going to determine the arc length. Find arc length. Yeah. The following function: 3/2 x to 2/3 power, and we are looking between 1 and 8. So just like before, I'm going to first investigate what this thing looks like, kind of see how it feels, how it looks, and then see if it actually integrates the function correctly. Here we go. But first, talk about this function. Desmos. Here we go. 3/2. Two-thirds. Oh, look at that. Beautiful, beautiful function.
Oh, it's like a little butterfly. Flower bleeding.
How is your arm bleeding?
What?
Why is your arm bleeding?
It started itching, so distracted.
Okay, we're investigating the length of the curve specifically from 1 to 8. So from 1 right here to 8 right there, we're seeing how long this length is. Ready? So same process as before. I'm going to determine how to find this function by looking at that specific integral, the square root of 1 plus y prime squared. Let's do it. Do the integral of 1 to 8 of the square root of 1 plus the derivative squared. So I start by finding the derivative of this function. The derivative of this function is, let's see, y prime will be equal to x to the negative 1/3 power. Multiply by the power, subtract 1 from the power, the 3/2 and the 2/3 cancel, and then subtract 1 from the power, leaving x to the negative 1/3 power. Yay. Okay. From here, and then put in x to the negative 1/3 power. And I start trying to see how I can simplify this function down. Now, for this specific function, there's a couple ways I could try to do it. Let's see, I could try to do some kind of u substitution. I have to be kind of creative in how I pick my u, but I think it could be done. Let's see, I could see if it matches one of the pre-made forms. I think that square root is one of the known ones. I could try to algebraically manipulate this to see if it comes up to something a little bit different whenever I do so. I think any of those would be okay. Some might be better than others, of course. So, what do you guys' thoughts? How am I going to simplify that function?
Don't.
If this is a calculator problem, I'd immediately grab a calculator and start plugging it in. Like, don't waste time on trying to integrate this function. If it's a calculator problem, just go ahead and grab it and plug it in. If it's not, well, I'd probably run to algebraic simplification first.
Just trying to rationalize it.
Yeah, which would probably suck, but I tried it. See what happens. So, it's a calculator question homework, so I'm assuming it's a calculator question for an AP test, so I'll grab a calculator out and see what happens. I'm going to integrate this function from 1 to 8 of the square root of 1 plus x to the negative 1/3 power squared dx. Here we go. Grabbing calculator. You're my best friend. Math. Finite integral from 1 to 8 of the function the square root of 1 plus my function x to the negative 1/3 power squared dx. So let's see what we get. Hopefully something nice, but I doubt it. 8.3519. Yay! Yay! If it's a calculator portion test, use the calculator. Okay, there is, I hate to say it, but there's a certain amount of arrogance that comes up sometimes when we take an AP style test like this, or a little math test where you're like, no, I need to solve this by hand. I must solve it by hand. Yes! No. Just do what is necessary to get the question right. You can be all moral and uppity and high and mighty later. I will teach you all about that. I remember my first time taking the AP Calc test, I was like, I'm not going to use my calculator ever this entire time. I didn't finish. They still had 2 problems left when I was at the time right now. And that was when I was a high school senior, so like, it wasn't any better than you guys. But like, I just grabbed the calculator and used it to solve some of the problems that would have been okay.
What'd you end up getting on it?
3. Which I was happy with. I was ecstatic with that. As well, I was like the highest score ever for my school. So I was like, okay. Like I said, we're not gonna have any really homework for this. I'll talk some more about it tomorrow. Do a couple more examples. Mainly because every year there is at most one question as of arc length. I rarely ever see it on the AP exam, and so I didn't want to assign a lot of it. But these are the 3 main applications of integration, besides the physics ones we've already talked about. And we'll go and do physics ones. That's all next week is physics applications. We'll be doing physics applications of derivatives. We'll be doing physics applications of integration. It's a good time. Yeah. Tomorrow, I might just make 3 of your homework problems into a short quiz. Take like 1 from 7.1 and 1 disk and 1 washer from 7.2 and turn it into a quiz for tomorrow.
So what?
Yep, tomorrow's Friday.
Oh wow.
Yeah. This week's kind of felt a little fast. Does anybody else feel like April's going quickly?
The March is beginning. Well, for us.
The March has ended. It's April now. Yes!
Yeah, I'm sad.
Okay, so we'll have a short, like I said, there'll be 3 questions. It'll be open notes. Like, I want you to get great on this. I want this to be a great boost for you guys. If you get your homework done, you can bring it and use it on this quiz. Okay, please do so. I want this to help you guys grades. Alright? And I want you to feel confident coming into it and try it out. Okay? Like I said, I'll put 1 problems in 7.1. It'll probably be a double curve. It'll be 1 on top and 1 on bottom. Those are the hard ones. It'll be 1 disk method, there'll be 1 wash method. Any questions to finish up today? Any other ones from 7.1 or 7.2 you need to see? Now that I've said that, and you're like, oh, I need help before I have a quiz on it.
31 on 7-1.
31 on 7.1.
Yeah.
Alright, I got you.
They're not doing the best of paying attention. No, they least that. Yeah.
Okay, 31 on 7.1. Okay, number 31 states, sketch the region bounded by the graph of the algebraic function, then find the area of the region. Yay, 31. The function is f of y equals y squared, g of y equals y plus 2. So I have the function f of y equals y squared, and then I have the function g of y equals y plus 2. So I'm going to graph these 2 functions and see what they look like. So this first function, the y squared function, if I write it in terms of x, it's kind of obvious what this function is. So remember, this should just be x equals y squared, and therefore we'd end up with y is the square root of x. So the first equation, which I'm going to call f, looks like a square root function. That is f. Okay. G of y is y plus 2. Again, I do the same trick over here. I turn this into an x this time, and I get x equals y plus 2. So to solve for y, I subtract the 2 over. I get x minus 2 equals y. So if I'm sketching this, that's a linear function, move down 2. So end up with the following. Move it down 2. And it's proceeding linearly like so. Now the difference between these 2 is that for this function, the squared function, unlike a square root function which stops, the y squared should continue down below. Just like x squared is a parabola, y squared is a parabola. Okay? So from here, like it's kind of obvious which one needs to go on top and bottom, and we can see there's clearly two intersection points. So I'm going to go in order as we talked about on Monday, which is I will find the intersection points first, and then after I find the intersection points, I will then determine which one is on top and which one is on bottom. Here we go. Intersection points. So remember to find the intersection points. I take the two equations, y squared and y plus 2. I set them equal. From here, I then solve. I get y squared minus y minus 2 equals 0. I can then factor. I could use quadratic equation. Either way, I get y minus 2 and y plus 1 equals 0. So we do with the following two solutions, 2 and negative 1. So those tell me my boundaries. Next, I need to determine which one is on top and which one is on bottom. Because I have sketched this, I have a good idea of which one is on top. Remember, it is about which is farthest away from the axes. That is the one that goes first. And the one that is closest to the axes, that is the one that will go second. So remember, it's the y-axis I'm doing everything with, so I'm looking at this line. So I ask myself, as I approach this line, which one's farther away? Well, as I approach it, I hit the blue line first, and then I hit the green line, no matter where I go. So that means I would do the blue equation, which is the y plus 2, as my top equation, my capital R, and my green equation, which is my y squared, as my lower equation, and now I have my integral. The integral from negative 1 to 2 of y plus 2 is my first equation, minus y squared, that is my second equation, and I've done everything in terms of y, so it's dy. And I'm going to get my function. I'll simplify it algebraically first. I end up with y plus 2 minus y squared. Weird. So I integrate. Y becomes 1/2 y squared. Plus 2 becomes plus 2y. Negative y squared becomes negative 1/3 y cubed. Evaluated from negative 1 to 2. Any questions about that integration? It's pretty standard power rule. Now I plug in 2 and negative 1. So I plug in 2, 1/2, 2 squared plus 2 times 2 minus 1/3, 2 cubed, minus 1/2, negative 1 squared plus 2 times negative 1 minus 1/3, negative 1 cubed. And then I start to simplify algebraically, or I've got to calculate and figure out my solution that way. 2 squared, 4, 1/2 of 4, 2, plus 2 times 2 is 4, minus 2 cubed is 8, minus times 1/3 would be negative 8/3. Minus. Negative 1 squared is positive 1, times 1/2 would be minus 1/2. 2 times negative 1 would be negative 2, but is it negative, so it becomes a positive 2. Negative 1/3 cubed would become negative 1/3. Negative 1/3 times 1 would become positive 1/3, but then I'm subtracting, so we end up with negative 1/3. A bunch of little math here. And then I combine these together until I have a solution. 2, 4, and 2 gives us 8, minus negative 8/3 and negative 1/3 make negative 9/3, or minus 3, minus 1/2. 8 minus 3 is 5, minus 1/2 would be 4.5, or 9/2. That's my solution. Gotta find them. The points of intersection. Yay. This thing's actually a pretty weird looking function if you spin it the way we're talking about. No, don't spin this. Just so if you were to spin this thing, it has a weird donut shape. It's kind of nice. Looks like a really crappy donut. Any other questions from 7.1 or 7.2? Those will be the two parts we pull from to have a little short quiz tomorrow. Okay. I will post about the homework being due.